Okay, I found my mistake. Now, if you remember what we were doing, it order by order. So this was the h to the 0 order. We solved this one. Then we have the h to the first power. At that order, we have this equation, and we solved it to obtain S1. There's no approximation up to here. Then we ignored S2. Then the question is, to estimate S2, what we need to do is just obtain the equation up to the order h bar squared. Now, if you do that, this seems to be the equation satisfied by S2. So you see there are two problematic regions. One is the logarithm of p, the other one is p prime over p. Well, there are some missing factors over there. You have to fill in the factors. Now, if p goes to 0, that is close to the turning points, you see that S2 is non-zero. S2 prime is very large. That means S2 will be getting large. Or if p prime over p is large, then again, S2 prime will be large and S2 will start getting large. And p prime over p is nothing but d lambda by dp, lambda prime over lambda. This is basically the rate of change of lambda. So the wavelength shouldn't change much. Well, the rate of the change of lambda is determined by the change of the potential. So if potential changes significantly, then lambda changes significantly. So that is why the potential shouldn't change much, or shouldn't change fast. If it is changing, it should be changing slowly, so that we can neglect S2 prime away from the turning points. So now let's come to the connection formula. So we have this general expression for the approximate expression for our wave function for an arbitrary potential. This is true for any potential. This is an approximate solution. And of course, we said that we have to somehow match this C, D, E, and F. And in order to do that, we have to find some formulas, some relations connecting the solutions to one side of the turning point to the solutions on the other side of the turning point. So let's look at the connection formulas. So we will be basically, let's look at this region where this is our energy. So here we have a turning point. And let's just say that this is x is equal to 0. We can just shift our x is equal to 0 point so that it corresponds to our turning point. Now the potential close to this turning point the potential will be just its value at the turning point plus its derivative at the turning point multiplied by x. Close to the turning point, this is the approximate potential. Well, we can put it in our Schrödinger equation. This is equal to E of psi. Or we can say that this is minus h bar squared over 2m d squared psi by dx squared plus v0 plus v0 prime of x minus e psi. This is equal to 0. We can just rename this variable. This is v0 plus v0 prime x minus e. This is our new variable. Now, in terms of this new variable, d by dx will be dx by dy times v0 prime, whatever that v0 prime is for our potential. No, sorry, d by dy times v0 prime. So our Schrödinger equation just takes the form minus h bar squared over 2m v0 prime squared d squared psi by dy squared plus y psi. This is equal to 0. Well, let's also make one more change of variable. Let's say that y is equal to alpha times z. If we put it over there, minus h bar squared over 2m v0 prime squared 1 over alpha squared d squared psi by dz squared plus alpha times z times psi is equal to 0. Let's just choose alpha cubed is equal to h bar squared over 2m v0 prime squared with the minus sign. And so we have the equation d squared psi by dz squared plus, now if I make this, yes, z psi, this is equal to 0. Now what I did is I just factored out the alpha. This is alpha cubed. Alpha was some kind of an arbitrary number that I chose. So if I choose alpha cubed as minus h bar squared over 2m v0 prime squared, the coefficient over here just becomes 1, and this is my equation. We know the solutions of this one? Well, these are the area functions, and there are two of them. One is called AI. The other one is called the BI. We have two solutions. And if you look at their shape, can you guess their shape? What would they look like? As a function of z. We know their equation. This is the equation they satisfy. So by just looking at that equation, can you guess what their shape would be more or less? Yes, that's one of the AIs, but in general, how does AI behave, let's say? Now, you can also look at the potential. I mean, you can also use your physical intuition. Let's say this is a linear potential, and we started by assuming the wave function has this form. Assuming the potential has this form, and this is our energy. So what would the wave function look like in such a case? Well, the wave function will decay exponentially in this region, and there will be oscillations on the other side. Now, the oscillations, when the momentum, the wavelength will also be changing. It won't be a constant wavelength because the momentum is increasing as you are going away from the turning point. So if the momentum is increasing, that means the wavelength is becoming smaller and smaller. So it will have such a shape, more or less. This is called the AI. Now, BI, it's also similar, but that's not the unphysical solution. It is still oscillatory in this range. Well, because if you see z is less than 0. Now, if z is positive, you see this is positive z. Because if you remember our definition of alpha, in this case at least, in this case v0 prime is positive, so alpha is a negative number. So z is a negative number times x, so this is the increasing z direction. And BI is exponentially increasing. Now, when z is negative, the equation tells you that the derivative of the function is proportional to the function with a, of course, changing but negative number. Now, if z is positive, if z is positive, then the second derivative is the function itself times some negative number, which itself can be changing, but nevertheless it's negative. So that is the characteristic of an oscillatory solution. So if z is positive, then it is oscillatory. If z is negative, it just means that the second derivative is just psi itself times, okay, if z is positive, a negative number times, no, the second derivative is, okay, if z is positive, it is oscillatory. If z is negative, the second derivative is the function itself times a positive number, which might be changing from point to point, but that is also either an exponential decay or an exponential increase. So we have these two possibilities if z is negative. And those two possibilities correspond to AI and BI. Now, of course, we also can say that if this is our potential, then our solution beyond this point should be the decaying one with increasing x, and the one over here should be the one that is increasing with increasing x. Those are the solutions close to our turning point. So that kind of gives us our solution. Now we already know the approximate solution everywhere. This is our approximate solution everywhere, away from the turning points. And now we have our solution close to the turning points. And the only thing left is how do we match the two. So we should be able to match the two. Now, here we will be doing some, let's say, trick in the sense that, okay, we are away from the turning points. Now we know the solution. We need to use that solution to match these two. But if we want to match, let's say, D, E, and F, that is close to one turning point. I mean, D and E this is our turning point. So here we have the D and E, so the solution with the parameters D and E. On the other side, we have the solution with F. And here we have the solution which depends on C. So we want to be using this area solution to match D, E, and F. So if we want to be able to match these things, there should be a region where both this approximate solution and our solution in terms of D and E, they are both valid. If our approximate solution for D or E is valid, then we can, now if our area solution is valid, then we can use the linear potential approximation in that region. If the potential is linear, then we can integrate the momentum integral. So let's see, this is what we should do. We need to evaluate this PDX somehow if we want to match these solutions. And if you remember, the P was nothing but 2m E minus V, V of x. Well, without knowing V of x, we cannot do anything. But since we want to be using this area solution to match two different regions, area solution is valid only in the region where we can expand V linearly. So that is what we will assume here. In the matching region, that is in the region where our approximate solutions is valid, and also the area solutions are valid. So we will assume that such a region exists. In this region, I can integrate P dx, and that would just give, using the linear approximation for V, 2m E minus V0 minus V prime 0 x dx. And the integral of this one will be just 2m E minus V0 minus V0 prime x raised to the power 3 over 2 times 2/3 divided by 1 over minus 2m v0 prime. Right? Well, I will do even one more thing. Note that E and V0. E, what is V0? In terms of the other parameters we know. This is the definition of the turning point. So we know the PDX integral. This is equal, well, let's say this is proportional to x to the power 3/2. This is what I will pay attention to. So the solutions, approximate solutions will be, it will contain an e to the power I x 3/2 I over h bar with some coefficient plus e to the power I over h bar minus e x to the 3/2 with some other coefficient. On the other side of the potential, now, so hold on a minute. So what we are actually doing is V0 prime, is it a positive number or a negative number? Well, it's a positive number, V0 prime. So if it's a positive number, so P dot dx integral is basically I times x to the 3/2, right? If x is, well, x can also be negative. You see, x, the turning point is x equal to 0. On the right of the turning point, x is a positive number, so p dx is an imaginary number. On the left-hand side, x is a negative number. So x to the 3/2 is a negative number. So p dx is a real number. So that is also what we are looking for, because onto the left of the turning point, we want to have an oscillatory solution. On the right of the turning point, we should have a decaying solution. Now, on the right of the turning point, this is on the left. Hmm?
We took the PDX integral and said it's proportional to Ix to the power 0 to. And this additional I.
This is not an additional I.
No, not that one. I mean,
this one.
You should have like I squared maybe.
Now, you see, we have this approximate solution. Now, here, P is a real number.
And there is another I there.
Now, P is a real number. P should be a real number. And on this side, P is an imaginary number. Now, what region 2 and region 3, region 2 correspond to negative x, region 3 corresponds to positive x. Okay, so now let's come back here. Now, what we had seen is that P dot dx integral is proportional to minus V0 prime x to the power 3/2. This is what we know. Okay? And V0 prime is positive. So, or this is equal to minus x to the power 3/2. This is proportional to, let's say. Now, if, yeah, on the right-hand side, we have this I, or if you want, I can just put this minus x to the 3/2. Which is a real number. So this is our oscillator solution. On the right, our solution is f e to the power minus some coefficient x to the power 3/2. This is on the right. Now let's look at the area functions. This is our approximate solution on the right of the turning point, or on your right of the turning point, where the classically forbidden region. Okay, you shouldn't memorize the area functions. So the properties of the area functions are asymptotics. AI of z is equal to some coefficient times e to power minus some other coefficient x to the power 3/2 as z goes to infinity. And bi of z is equal to some coefficient times e to power plus the same coefficient raised to the power 3/2. Okay. So one thing that we know, well, we know that the solution on the right has this form. So if the solution has that form, I can say that bi should be 0. The coefficient of bi should be 0. So that tells me that in the matching solution, where let's see, here we have our matching solution. B is 0. Just by matching it on the right. Turning point tells me that B should be 0. And also, it also tells me what A should be. A should be proportional to, because A, there is only this term left, and the constant coefficient over here, which is A times, the coefficient of my solution on the right-hand side is A times this coefficient. But my solution on the right-hand side is this one, which should be F. So which basically tells me that A should be equal to square root of 4 pi over alpha h bar times F. Now, okay, if you just put in the coefficients, etc., I will be skipping those. So we know what A is in terms of our solution on the forbidden region. But this solution is also it should be our solution in the allowed region. And that tells us that the AI, we should use the other asymptotics, AI of z this is approximately 1 over square root of pi minus z to the 1 over 4 sine 2/3 minus z to the 3/2 plus pi over 4. Now our solution on the right-hand side, or we can even write it in terms of exponents, 1 over square root of pi minus z to the power 1 over 4, 1 over 2i, sine of, no, not sine, e to the power I, 2/3 minus z to the 3/2 plus pi over 4 plus e to the power minus I times 2/3 minus z to the 3/2 plus pi over 4. We also know what A is in terms of our solution on the forbidden zone. This is our solution on the allowed zone. But if you look at our solution on the allowed region, our solution on the allowed region is this one. So we have this minus, well, x is proportional to z, or z is proportional to x instead of x, we use the z. We have both of these exponents, as these ones, these two. Well, there are these unknown coefficients, d and e. Well, those unknown coefficients are already known on the other side, so we know what, and just comparing the two, you can extract what d and e should be in terms of f. Well, we had this f, unknown f. In terms of this unknown f, we found the coefficients. Unknown f is nothing but our solution in the forbidden zone. In terms of this unknown f, we found our matching, the coefficients in our matching solution. We saw that b should be 0 and a should be something proportional to f. So we have this matching solution. And then once using this matching solution, we matched it to our solution in the allowed region, which depends on d and e. So we can express d and e also in terms of a, which is related to f. So we have this overall coefficient f, which is nothing but our normalization. So both d and e we can write in terms of f by using this matching function. Well, I'm not putting in the coefficients over there because I don't think it will be illuminating it. And it will be just boring mathematics, which you should do on your own, which you will do on your own in the homework.
Phase term.
Which phase term? Well, those will be the phases of f and d. Pardon. Oh, sorry, d and e. So d and e will contain those pi/2 factors. We don't know what those are, but it will contain those ones. So here this is. Yeah, you can just factor out this e to power I pi/4, and you just get an overall factor of I, relative factor of I. And this e to power I pi/4, that's the overall phase. And of course you have to repeat this for the left-hand side. With V0 prime negative. Well, V0 prime positive and negative will just make sure that your area solutions are oscillatory in the allowed region and they are decaying in the forbidden region. And that is something we want. And that will be there. And of course, you can just find the solution by matching the turning point on the left. You can find the solution in the allowed region by matching at the turning point on the right. So you have two solutions in the interior region, and they should agree with each other. Well, let me just write down what those solutions are. Now in the allowed region, we will, by just matching in the two turning points, here we already determined one of by matching at the turning point on the right, we determined what is the shape of our wave function in the allowed region. And in fact, it's just the AI function. This one. And the solution just is in the allowed region by matching at the turning point on the right. Psi of x is proportional to, I have some normalization constant, 1 over square root of p of x times sine of 1 over h bar from x to, let's say, x2, p of x prime dx prime plus pi over 4. x2 is the turning point. And on the other hand, by matching at the other turning point, we have the solution psi of x, which is proportional to sine of minus 1 over h bar p x prime dx prime minus pi over 4. And the limits here is from x1 up to x. So we have these two solutions, and these two solutions should be the same. They should agree with each other. So this basically tells us that 1 over h bar integral from x to x2 p of x prime dx prime plus pi over 4 should be equal to minus 1 over h bar from x1 to x px prime dx prime minus pi over 4 plus a multiple of, I would say, 2 pi. Pi. It will also 1 over square root of px. Otherwise, they won't agree. If this is satisfied, these two solutions will differ by a phase, and you can just choose your coefficients such that the phase will also agree. You see that here in the equality we have one coefficient. Here we have a different coefficient because we are matching two different solutions. So it's fine if these two solutions differ at most by a phase at every point x. So that's a common phase. So if that is what we want, it's enough that they differ by a multiple of pi rather than 2 pi. D need not be equal to d prime. D can be minus d prime. So that's why we have this multiple of pi. And now if you just combine them, you have 1 over h bar. I'm just moving this term to the right-hand side. I have an integral from x1 to x plus an integral from x to x1. So we have an integral from x1 to x2, p of x prime dx prime. This should be equal to n pi plus pi over 2. And we are back to the Bohr condition, basically, beside that factor of pi over 2. But also just keeping in mind that these WKB approximate solutions are valid for high energy. The wavelength should be small, so that any change in the potential happens in several wavelengths. So for large, and that pi over 2 factor will not make any difference anyway. So, and these are the condition. These are the, in fact, this equation tells you the energy eigenvalues. Questions? Now let me just go over, just ignoring the technical details, let's just go over what we had actually done. So we are looking for an arbitrary potential. It doesn't have to have a bound state. I mean, you can apply this for a tunneling problem, for example. There's an application in your book also. You can apply it to any system for any potential, as long as the wavelength is small compared to the characteristic length of the potential in which the potential changes significantly. In that case, if you just take this as an example that we have been studying, you find a solution that is valid in this region. You find another solution that is valid in this region, and you find another solution that is valid in this region, away from the turning points. So these are our three. Here that we have the oscillatory solution. Here we have the decaying solutions. Then, of course, we have to match them. And the matching is basically done by finding a new set of solutions valid in this region and another set of solution valid in this region, close to the turning points. So we have these regions where both of our solutions are valid. The matching solutions and the WKB solutions. Let's see. In these crossed regions, both kinds of solutions are valid, and we can use, they should be valid. Such regions should exist if you want to apply this method. And if in this region both of the solutions are valid, they should be the same solution. And from this requirement, you just determine your coefficients. First, you determine the unknown coefficients. That is, in the intermediate region, we have two possible solutions, one moving to the left, the other one moving to the right. We have these two solutions. And outside, we have decaying solutions. They have a priori unknown coefficients, which you have to determine. And you determine them by using these red matching functions. And the last thing you have to do is that the matching you have done on the left turning point and on the right turning point, they have to be consistent with each other. And this consistency requirement is what gives you the energy eigenvalues. Without this consistency requirement, the E can take any value. But only for certain values of E, the matching on the left turning point will be consistent with the matching on the right turning point. That is how you obtain the discrete energy eigenvalues.
What if there is another crystal potential?
Then you just repeat it. Well, let's say you have this famous double valve potential. And if this is your energy, you have this region, you have this region, you have this region, and this region, and also this one. And then you should do the matching. There's a matching here, there's a matching here, another matching here, another matching here. And in these matching regions, the potential is, you just approximate them by linear potentials. Well, of course, the matching regions are a bit exaggerated over there. But the idea is basically the same. So you find approximate solutions away from the turning points, and using area functions, which are the solutions for a linear potential, you match them. And to get the energy eigenvalues, your matching should be consistent. In fact, you can just go one by one. You first match here, using that solution, match here. And even in the previous case, I mean, rather than matching the two independently, you can say that you match one first, you match here first. After the matching, you know what the solution is in the intermediate region, in the allowed region, and then match that one to the solution over here. And if you do the matching, in general, the solution in the other matching region will have a decaying part and an increasing part for a general value of energy. Then it is the normalization condition which will give you, normalizability condition which will give you the energy eigenvalues. Only for certain values of the energy eigenvalue. Once you match this one, then you match here, you get a normalizable solution. Probably in this double valve potential, that would be the easier one. And just go one by one. I mean, rather than using 1, 2, 3, 4 independent matching conditions, you start with one of them, and using that, find the matching solution in this region, and using that, using the matching solution in this region, and using that, find the matching solution in this region. And the matching solution in this region should decay exponentially. The exponentially increasing part should cancel. That will give you the energy eigenvalues. There is one catch though. not so bad. This expansion of the areas. Where did I have them? Yes, this one. You see, they are valid away from the turning point. So, I mean, there were several assumptions that we were making. Okay, one is that, okay, this e to the power integral of p dx approximate solutions should be valid in our region. In certain regions, they are valid. And then we have these area functions, which are valid close to the turning points. And we assume that there were regions in which this our approximation solution e to the power integral of p dx is valid, and also the area solutions are valid. So in the regions where e to the power ipx, in their boundaries of their validity, let's say, the potential should already behave almost linearly. Furthermore, this linear region should be large enough such that so that we can take this limit. The areas do behave like this at the joints, at the regions where both approximations are valid. But of course, this is z is equal to minus infinity, and if you remember, z was defined as alpha times x, right? No, sorry, z is y over alpha. So z goes to infinity can be y becoming large or alpha is small. So if alpha is sufficiently small, then we are also safe. Well, what does alpha small mean? The derivative of the potential should be small. It's basically the same condition. The potential should be changing slowly. As long as the potential is changing slowly, there is a region where we can assume the potential is linear. And in the same region, the areas are our e to power p, the integral of p dx solutions are valid. And at the same time, areas behave as if they are in their asymptotic form. They behave like this. So basically, we have one condition, that the potential should change slowly. So although this is something that one should pay attention to, but once all the approximation is already based on the fact that the potential changes slowly, doesn't change at all, let's say, within a couple of wavelengths. So if that assumption is satisfied, all of the other conditions are automatically satisfied, kind of. And another way of making sure that this condition is satisfied is that lambda is small. You have an arbitrary potential which have variations, but lambda can be small. And lambda is small if the energy is high. So that is why this approximation is in general valid for states with high energy, much higher than the potential energy. But if, for example, V is constant, we have the double well potential, this is exact anyway. Yes, any questions? Okay, then you will probably receive your homework today or tomorrow on the WKB. On Tuesday we might do some examples, and next week we will start the time-dependent one. It's more fun. No, time-dependent perturbation theory.